For this bottom example, we're supposed to write an equation of the tangent line to this function at this point that's on the function. So the objective is to write an equation of a tangent line. So I'll start here. We need point slope. So here we have x sub 1 and y sub 1. It's really a t and an f of t, but I'm just going to go ahead and use x sub 1, y sub 1. So notice the only thing that's missing is the slope, m. We get the slope from the derivative, so it didn't tell us straight up to find the derivative, but within this question, we just have to know if we're writing the equation of a tangent line, and they give me the point that I have to find the slope, and that comes from the derivative in calculus. So let's find f prime of t. So I'm going to leave a little space here so we can go back, and once we find the slope, m, from the derivative, we can insert that and then finish this question. I'm going to leave a little room like this. All right, let's find the prime at t, f prime at t. So the limit as, and we'll just call this the change in t then. We'll just change all our x's to t. So then it'd be f of t plus delta t minus f of t. How about if I write delta t all over delta t? If you're comfortable changing everything to x's, there's nothing wrong with that. All right, so we have to insert t plus delta t into the equation for all the t's we see. So that it's going to be 2 over, where this t is, we'll put in t plus delta t, and then the minus 1 is still in the denominator, minus the function of t, so f of t is 2 over t minus 1, all over delta t. Okay, if we try to plug in 0 for the delta t's, we're going to get indeterminate, so what do? It's not obvious like the previous problem where we did some distribution. It's not obvious like the previous problem where we had square roots and we multiplied by a conjugate. This actually requires a different algebraic skill. In order for us to kind of clean this up, we need a common denominator in the numerator. So here's our numerator. So to get a common denominator, I'm going to multiply this left fraction by the denominator t minus 1 over itself. And then over here, I'm going to have to multiply this fraction by the other denominator, t plus delta t minus 1. And then we'll want to populate that on the top because we're multiplying by a form of 1. Okay, so in the numerator, when we multiply these two fractions together, we'll just multiply 2 times the t minus 1. So 2 parentheses t minus 1, and that's all going to be over the common denominator of t minus 1 times parentheses t plus delta t minus 1, minus the other fraction. And it's going to have the same common denominator. Let's put those in parentheses, t minus 1, t plus delta t minus 1. We won't multiply those two together. We're looking for something to cancel. And then on top, it's going to be 2 times parentheses t plus delta t minus 1. And still all over delta t. The algebra on this is a little bit cumbersome. Okay, so I'm going to make this all one fraction when I subtract these two. So combining the fractions over the common denominator. And then we still have a delta t down here for this denominator. Let's go to the numerator and distribute. So I'm going to get 2t minus 2. Now be careful over here. I'm going to do two things at once. I'm going to distribute the 2, but I'm also going to take it as a negative 2. So that's going to be minus 2t minus 2 delta t, and then a plus 2. It's easy to kind of forget these signs right here. Let me do a little cleanup. It looks like the minus 2 and the plus 2, And it looks like the 2t and the minus 2t are going to cancel. Let me come up here. Okay, so what I have left is negative 2 delta t over the common denominator t minus 1, t plus delta t minus 1. And this is still all over delta t. So what we should do here is probably put this denominator over 1, and then we're going to actually multiply by the reciprocal to the top fraction. So remember, this is all on top, and delta t is what's in the denominator of that bigger fraction. So let me multiply by the reciprocal, so that'd be times 1 over delta t. And so this will be gone when you multiply by the reciprocal. And notice across these fractions, I can divide out the delta t and the delta t. They divide out by a 1. So let's clean that up before we insert 0 for delta t. So f prime of t equals limit delta t goes to 0. Let's see, if I clean this all up, I still have that negative 2 on top. And then the t minus 1, t plus delta t minus 1 down here. I still have a negative 2 on top. Okay, now let's put in 0 for the delta t so we can lose the limit statement. So f prime of t equals, so the limit statement's gone because I'm about to insert 0 here. So I have negative 2 on top, t minus 1, and then this would go to 0, so I have another t minus 1 parenthesis. So rewriting that, f prime of t, the derivative, the slope on f at t is equal to this formula, negative 2 over parentheses t minus 1 squared. So that's the derivative. So remember, we need the slope still to finish this equation. So how do I get the slope? Well, we plug in the t value. In this case, I called it x sub 1. So now let's find the slope of this graph at x equals 0, or t equals 0. So f prime of 0, I've got negative 2 on top, 0 minus 1 squared. That'll be a positive 1 down here. So the slope of the graph at t equals 0 is negative 2, also known as our m value. So finally, this little space we have here, we can complete this equation. So it's y minus negative 2, or y plus 2, equals negative 2, the slope down here, times parentheses x minus 0. And you can, of course, clean that up if you want, but we'll just say that's a safe stop, and that should be our answer. All right, so I think the challenging part on that may have been like simplifying these complex fractions. And for a little more study on that, you can always YouTube and search for simplifying complex fractions. That'll give you a little more practice if that's an area of struggle for you. Any more yet? These two problems are the same types of problems, just different functions and lines are given. So I think I'll do this problem right here. Online, the posted solutions for this problem can be found. And so if you want to try and do this second one here, then at least you have something to kind of look at and kind of guide you through it. All right, so it says find an equation of the line that is tangent to the graph of f. So here's f. We want to find an equation of a line that's tangent to this graph, but it's parallel. This tangent line has to be parallel to this other line right here. So find an equation of a line, that means point slope. So we'll be using point slope to write an equation to a line that's tangent to this graph but parallel to this line. Well, two lines that are parallel have the same slope. So this line is given to us so that we can find its slope. So let's solve this linear equation for y. I think I'll take and add a y to the other side, making this y positive. That'll leave 6x plus 9 equals y. So this is in what we call slope-intercept form, so y equals 6x plus 9. So this identifies our slope, our coefficient on x. So this is our slope value, that's m. And if you remember from our work and what we've been doing in this lesson, this slope can also be called f prime. It's just I don't know at what x value the slope of this graph is 6. I mean, I can kind of guess if I graphed x squared, something like this, I would know that probably somewhere around here, the slope of the graph is 6 because that tangent line appears to have a slope of 6. So I bet the point's over here. I just don't know what that point is. So again, I'm supposed to write the equation of this tangent line that has a slope of 6 because it's parallel to this line. I have to write the equation of this line. Well, remember the point slope formula is y minus y1 equals m times x minus x sub 1. So right now, all we have is m, which is 6. So at least I have 6, but I need to find the point that this slope is 6. All right, so how do I find the x-coordinate, the y-coordinate, where the slope is 6? Well, we actually have to go through and find the derivative of this function and set that equation that we get, that derivative, equal to 6, because I want the slope to be 6. So we're going to find the derivative, set it equal to 6. That will get us the x-coordinate of this point. Once we have the x-coordinate of this point, we can plug that x value back into the original equation, and that'll give us the y-coordinate at that x we found. So we've got to find the derivative and set it equal to 6. Okay, the function we're working with that we want the derivative of is x squared, so plug in x plus delta x for that x. Square it. There's nothing else in the equation. Then minus the function x squared. All right, so from a previous problem, when we squared this binomial, we got x squared plus 2x delta x. Easy to forget that x. Plus delta x squared. That comes from FOILing, distributing, and then minus x squared, and then still all over delta x. So this x squared will cancel with this x squared, leaving terms which is delta x that we can factor up front. So let me come up here. Limit is still part of this painful process. Okay, I'm going to factor up front a GCF of delta x, so that leaves me 2x and a delta x. That's a mess. Delta x's divide out, ready to plug in 0 for delta x and lose the limit. Plug 0 in for that delta x, so our derivative is 2x. Okay, so the ultimate objective is to write an equation of a line. We've got the slope of 6 from putting this linear equation in slope-intercept form. We just need an x and a y coordinate. Well, we do know the derivative is 2x, so this is actually equal to our slope. So let's set f prime of x equal, let's set 2x equal to 6. So 6 is our slope, that's what the prime gives us, equals 2x. Divide both sides by 2. That wasn't too painful. So what that tells us is the x coordinate that has a slope of 6 is 3. So now I have the x sub 1 coordinate. How do I find the y when x is 3? So go back to the original function, That gives us y's. So f of x equals x squared. Plug in 3, the x coordinate, and we'll get 9. So the derivative gives us the slope, but the original function gives us a y coordinate. So now we have everything we need. This is x1 and y1. So y minus 9 equals slope was 6 here, times parentheses x minus 3. So you might want to practice with this problem right here. Where it's going to get kind of cumbersome is finding this derivative of that cube. But I think in a previous problem we did take x plus delta x and cube it. So we have that in a previous problem, so hopefully that work will be a little bit easier. Okay. This says use the alternative form of the derivative. Well, I haven't given you that yet, but I'm about to. It's actually somewhat of an easier formula to find the derivative. You're probably thinking, well, why haven't we been doing that? Well, it's an alternative form. It's not the formal definition of a derivative. And typically when we teach the calculus classes, we want to make sure that we have exposure to that formal definition of a derivative. All right, so anyway, here's the alternative form of the derivative. So how do you know when to use it? When they ask you to use the alternative form of the derivative. So instead of using the process we've been using to find the derivative at x equals c equals -5, instead of using that formula definition of a tangent line at a specific c, or using this and then plugging in our c value, okay, here is the alternative form. Do this first. The derivative, the slope at c is equal to, it's a limit, but we're not going to use delta x's. We're just going to say the x coordinate is going to, another x coordinate of another point is going to c, the x coordinate of the point I want to find the slope of the function f of x minus the function evaluated at that c value, all over x minus c. So a little bit different, alternative form to find a derivative. So let's see if we can use this formula to find the derivative here. And we're actually going to end up finding a numerical value, not an equation with an x in it, because we actually know the x value or the c value and where we want the slope. All right, so just kind of using this formula over here and customizing this formula. Everywhere I see a c, I'm going to replace a -5 in for it. And wherever I see the function, f of x, I'll be replacing the function I'm given. So f prime of -5 equals the limit as x approaches -5. In the numerator, we have the function, so it's x cubed plus 5x squared plus 5, minus the function evaluated at -5. So let me do that little side work over here. Let me plug in -5, my c value, in for all the x's in my function. So -5 cubed. That's a 5. So this is -125 plus, that's 25 times 5, that's 125 plus 5. So when x is -5, my y is going to be +5. So now we have this value, f of -5 here, which is 5. And it's all over x minus -5, or simply x plus 5. So as the x coordinate of another point gets closer to the x coordinate of -5, let's clean this up. We've got the 5s are going to cancel. And then we've got 2 terms with x, so let me write that down first. X cubed plus 5x squared over x plus 5. There we go. So let's factor the numerator. Now in this case, we want to be able to divide out the x plus 5 because that's giving us the 0 down here. So it looks like I can factor out an x squared, and I'm going to hope that what's left is x plus 5 to cancel with the bottom. So take out an x squared, that leaves x. Take out an x squared, that leaves plus 5. Whew. Okay, and then once we divide out these common factors, we can plug in -5 for x. So f prime of -5 equals, we'll lose the limit statement, -5 gets squared, and that'll be 25. So let me go back and read the question. Did I use the alternative form? I did. To find the derivative at -5, I did. So it's not a derivative, it's more the slope, because it's not an equation with an x in it. So this is the answer, 25. Ooh, the slope of that graph is pretty steep. Or the tangent line is pretty steep. The slope is large. Okay. And then finally, we need to discuss differentiability and continuity. Okay, hopefully you're taking brain breaks along the way because there's a lot of information. All right, so this page deals with differentiability and continuity. We all know what continuity means. It means you can draw, informally, it means you can draw a graph without ever lifting your pencil. So what does differentiability mean? Well, it says a function is differentiable if the derivative or the slope from the left and right exist. So if the slope from the left and right as you're coming into a point, if they exist, the slope exists of that tangent line, and they're equal. The alternative limit form of the derivative that we just used is useful in investigating the relationship between differentiability and continuity. The existence of the limit in this alternative form requires that the one-sided limits, the limit as x approaches c from the left and the right, exist and are equal. So these are slopes, and that's all this is saying. This is the notation that represents left slope, right slope, that they both exist, they're not infinities, and that when I find this limit, the slope from the left and the slope from the right, that they are also equal. So this is just words up here, and this is the notation that represents those words. Sometimes it's best to look at how differentiability fails, and it fails in, I've got 3 situations here. So a function is not differentiable when a graph is not continuous. So we're going to consider a function, the greatest integer function. That's what the double brackets mean. So I'll draw kind of a quick little graph over here. The greatest integer function is a set of steps, horizontal steps. So, and they cover a horizontal distance of 1 unless you do some transformations. But let's look at the integers 1, 2, 3, perhaps -1, -2, etc. And maybe up along the y-axis 1, 2, 3, or y-axis 1, 2, 3. And down the negative y-axis, -1, -2, -3, and maybe a -3 here. So the greatest integer function, it is on the calculator. You might have to go to catalog, but it is under another button as well. But you can go to the catalog and kind of find it on the calculator. But the greatest integer function actually is a set of horizontal steps. It starts at 0, including 0 with a closed circle. It covers a horizontal distance of 1, but when it gets to 1, it's an open circle. And then you jump up vertically to 1. Close on the left, cover a horizontal distance of 1. When you lined up vertically with 2, open circle. Jump up 1 unit, closed on the left, cover a horizontal distance of 1, open circle. And I can go backwards. I can do an open circle here, horizontal distance, closed circle. Jump down, open, cover a horizontal distance. And it just keeps going, okay, in this direction. So obviously this greatest integer function is not continuous. There's a lot of places you're going to have to lift your pencil. So we would say that f of x, this function, is not differentiable where it's not continuous. So it's not differentiable at, and we'll call the set of integers z. So every time you hit an integer, you have to jump. There's a break. So the slope from the left and the slope from the right they're actually, if we use the alternative limit form and set that's what this space is for. I'm not going to have time in this video to kind of go through it, but if you looked at the key online, you would see a proof of why this function is not differentiable, because the slope from the left is actually, the slope from the left is going to be positive infinity, which seems strange, and the slope from the right is going to be 0. So one doesn't exist, and they certainly aren't equal. So we can say f of x is not differentiable at all the integers. However, what we can say is that the function is differentiable, okay, on the intervals in between those integers. So for example, f of x is differentiable on, and I'm just going to do a dot, dot, dot to get it started. I'm going to use parentheses, and I'm going to say, let me start at -3, and where's it's down here. It'd be down here somewhere, closed on the left and open over here. It'd be differentiable on each individual piece. So -3 to -2, not including -2 to -1. So anywhere that you're on each piece, okay, it is, because if I chose this little point right here, the slope from the left and the slope from the right, they're going to be the same on that continuous piece. And I'll put comma and then maybe a dot, dot, dot to represent that. Now there is more that I put here, and it actually goes through using this alternative limit form of the derivative to prove at x equals 0 that the slope from the left and the right, one does not exist. The other slope is 0, so a function then is said to be not differentiable. Right. Another case where a graph would not be differentiable is when a graph has what we call a sharp turn. And to help us understand this, we consider the function f of x equals the absolute value of x minus 2. So here's an illustration. So the absolute value graph shifted right to, here's 2, is kind of a V-shaped graph. So I would say here f of x is not differentiable at x equals 2 at its sharp turn, but f of x is differentiable, f of x is, I'm going to abbreviate, no, I have room, differentiable on the rest of its domain. -infinity up to 2, use parentheses, and then 2 to infinity. So the only x value at which this graph is not differentiable is at its sharp turn, and that's because the slope as you come into x equals 2 would probably be -1, and the slope of the graph as you come into 2 is +1. It's always -1 until you hit 2. It's always +1 until you hit 2. But if you consider this point on this graph, as you come into that point, the slope's always going to be the same, probably -1 from the left and -1 from the right. So this function is continuous at x equals 2, however, the one-sided limits are not equal. So this graph is continuous across its entire domain, it's just not differentiable at the sharp turn at x equals 2. And here, this space was left for me to go through a little proof of those two slopes. Just don't have time in this video, but it is, like I said, this work is posted on the key on Canvas. All right, so far a function is not differentiable when it's not continuous, but there's parts of it where it can be differentiable, where the graph is continuous. So when a graph is not continuous, when a graph has a sharp turn, and then lastly, we'll look at differentiability fails when a graph has what we call a vertical tangent line. And to help us understand that, we're going to consider the function f of x equals x to the 1/3. That's also the same thing as saying the cube root of x. All right, so let's get an illustration of that. And that graph comes down from quadrant 3. It kind of comes in at the origin, and what happens is it gets very steep, and then it turns around in quadrant 1. So right here at x equals 0, if you were to draw a tangent line to this graph, part of it is to the left of the function, and the other part happens to be on the y-axis, is to the right of the function. It's vertical. Well, what we know about vertical lines is that the slope does not exist. And remember, way back up here, a function is differentiable at an x value if the slope exists. Well, this slope doesn't exist. This graph is continuous, just like this sharp turn graph is continuous, but we're not differentiable at x equals 2. Here, we're not differentiable at x equals 0, but we are differentiable everywhere else. So f is not differentiable, I will abbreviate here, at x equals 0. And you don't have to put the parentheses with the x. It's okay to do f or just f or f of x. F is not differentiable at x equals 0 because of that vertical tangent line, but every other tangent line is not going to be vertical, so f is differentiable on all other x values of the domain. All right, and one last thought that we need to take away from this page. I'll put the statement down here. It says differentiability implies continuity. So if we were told a function is differentiable, we then know that that function also has to be continuous. But the other way around, continuity does not imply differentiability. Meaning if I know a function is continuous, consider these last two examples. You see, these two functions are continuous, but are they differentiable at all x values of its domain? Nope, not at the sharp turn and at the vertical tangent line. So just kind of keep that in mind, that differentiability does imply continuity, but continuity does not imply that that graph is differentiable. And this space right here is also provided for me to, I was showing that using the alternative limit form of the derivative, that the slope at this tangent line went to infinity. So, which does not exist, and that's why we're failing differentiability.